Why is it so difficult to track asteroids? This is a question that has been asked of me a number of times. One of the big ones is Elon Musk's Tesla Roadster, which kind of looks like an asteroid, but asteroids in general are considered very difficult to track. And why is it that we have such a difficult time doing this? So I'm going to talk about why some of those reasons are and why this actually really matters. There's a couple of interesting asteroid news items that I'll talk about later that happened recently as well. And we'll hopefully be able to really get down to the bottom. In order to track an asteroid, you have to be able to see it, and you have to see where it's been through some period of history. One point at an asteroid won't even tell you that it's an asteroid. There were times where we had imaged planets, didn't realize what they were, and it took a number of years later for it to be observed again, for us to go back through the data and realize, hey, that strange object that Galileo saw, that actually turns out to be Neptune. It really happened, guys. So with one data point, you can't see the movement of the objects and you won't know that there's something else there. But if you take a number of pictures, you can see it moving along gradually. Once you see it moving, you know that it's a solar system object. Either that or it's an object that's going the speed of light, which is, of course, impossible. But it has to be something fairly close to us realistically for it to make a difference if you see it moving from night to night. When you see an object that's moving from night to night, you can start to calculate the trajectory. Now, one of the big problems is how accurate do you know where it really was? Well, a couple of things that can influence this. First of all, if you have some known stars that are in the sky when you're tracking this asteroid, you can use those as a reference point to exactly identify where on the celestial sphere you happen to see that. And if you're able to do this, that will give you a pinpoint accuracy to a sub-pixel level, actually. What you can do is, if you know the characteristics of your camera, you can determine to a sub-pixel level based off of the point spread function, the distribution of the light over from one point source, which pretty much all asteroids are, unless they're really close, over the pixel to determine where exactly it is. It's a pretty neat trick. Still, you're limited by the camera as to how accurately you can do this. You're also limited to the optics. The bigger of a mirror you have, the better your point spread function will be at resolving things. If you're able to adapt for the twinkling effects that cause from the atmosphere, because the atmosphere has all kinds of nasty turning around it, then you can bend the mirror a little bit to correct for these, and you can increase the resolution even further. But that only really happens on pretty high-end telescopes. You don't tend to have that happen for these backyard telescopes. All of these things cause a huge amount of uncertainty. If you're able to observe it for 2 months straight, for instance, you probably have a pretty good arc on it and you're able to compensate for some of these. You know that it has to follow the course of gravity. If you don't have a bright star in the field of view that you can easily identify, then it gets to be a little bit harder because it depends on how accurately you pointed the telescope. And it's really hard to point. I'm sure if you watch some of my videos from the past, you'll notice that the camera position changes slightly from image to image because I'm just not that good at pointing the camera exactly where it needs to be. And it turns out most people aren't. Unless you have someone who's really trained at that, then you're probably not going to be that accurate. So assuming you have a good arc, you can take the orbital mechanics formulas and calculate exactly where it is over a period of time, and you can figure out where it's going to be. Now, we can do this because we know the gravity of the sun, we know the gravity of the planets, which have the majority of influence outside of the sun, and you can do some pretty good accurate calculations. But anytime an asteroid flies relatively close to a planet, and it doesn't have to be that close, it just has to be within 1/10 of the distance from the Earth to the sun. It's not that far. If you get to be that close, then the trajectory will be tweaked very slightly. So there's a number of reasons why knowing the exact velocity and position is difficult. First of all, the limited arc will cause some degree of uncertainty with this. Second of all, it actually can change a little bit. See, there's at least two major factors that will change the velocity of an asteroid. The first one is the solar radiation. Now, anytime you're in light, such as these lights that are helping you to see me better, they're actually pushing me backwards. Now, the effect is so small, you can't really notice it unless you have a sensitive instrument with an object such as myself. But over a long period of time, and especially when you're not in the influence of an atmosphere or a planetary body like we are, that effect will have an influence. Satellites actually going around the Earth have very slight push due to this solar momentum that can happen, and it will perturbate the orbit slightly. And it happens even more. So what will tend to happen is all of the objects will tend to be pushed very slightly outward with time. The other one, though, is perhaps more interesting. It's called the Yarkovsky effect. And those of you who have been around for a long time know that this is probably my favorite effect, at least to say the name of the Yarkovsky effect. And it's a little bit tricky to understand, but let me bring a prop in here to help with that. So let's say that this is our asteroid. This is just a glass ball. Let's say that you have the light that's coming in from straight at the camera right at here. Now, if this object was not rotating, there would be a release of heat that would come in the same direction, more or less, that it came from. And those release of photons actually will generate more forward momentum. So it'll tend to be pushed out a little bit more. The Yarkovsky effect, though, is really interesting in that rotating objects, if it rotates 90 degrees, then that heat will come out from this side and it will tend to push it a little bit along the direction of rotation. This is a very difficult thing to characterize. It depends on the heat absorption and releasing properties of the asteroid, and you have to measure this specifically for each asteroid that you're going to care about. Now, it really only has an effect, along with solar radiation, for smaller asteroids in the realm of hundreds of meters or less, but it can have a dramatic effect. One of the news items that happened recently is my favorite asteroid, which is Apophis. That's a near-Earth object. It's going to fly by Earth in 2028, I think. It's going to come closer to us than the geostationary satellites. It should be naked eye observable for those who live in a remote enough area. If it passes in exactly the right spot, then it could come back and hit us in the year 2035. Now, it's been thought that that was the only time period that it could actually do this, but it turns out that as they were starting to measure the Yarkovsky effect for this asteroid Apophis, that in the year 2067, it also has a chance of impacting the Earth. Now, this is a very, very small chance, and we're not going to know any of this until it makes the flyby in 2028. But for a while, there was something on the order of a 5% chance that this object would impact the Earth. If it did, it wouldn't be like a dinosaur killer event, but it would cause some pretty serious damage to wherever it hit. And it's something that if we have the ability, then we would probably want to try to disrupt it. Now, I want to stress that the odds of it hitting the Earth are very little, but they actually do exist, and it is by further observing it that we can be able to make a better determination of this. The Yarkovsky effect was what made the difference between it hitting the Earth and not. There's another asteroid that actually happens to be the asteroid that we know about that has the highest chance of impacting the Earth, and that is the asteroid Bennu. Now, if the asteroid Bennu were to hit the Earth, it wouldn't do so until about 150 to 200 years. I think the earliest possibility is in the year 2175. And there's a number of very low likelihood passes from there for the next 25 years where it could impact Earth. It hangs out in that region around Earth, and so therefore could always impact us. And it's big enough where it would hurt. It wouldn't be an extinction level event, but it would knock out a continent if it were to hit. So we really don't want that to happen. But we were able to study it, and hopefully that data can be used to better know its trajectory. This is going to be an object we're going to continue to study. And we also took a sample of it, which had some interesting issues. Basically, the way the sample container worked is it blew out a bunch of air, and some of that air, based on the shape of the collection, would come back in and it would scoop up some dirt. What was supposed to happen is this collection arm, which is on the end of a long arm that it has, was supposed to close up, and they could actually try to measure this. But when they took a picture of it, they realized that they had a large rock that got stuck and jammed in there, so it couldn't close the door all the way. Now, this wasn't a huge issue, but they had to do a few things a little bit differently because they were leaking out some of this precious dirt that we can use to understand the solar system formation better. And what they had to do was pack it in the sample return container. They were able to do that quite successfully. It got closed off and it looks like the container's sealed, and now that is going to be returned to Earth. They're going to land it in the desert atmosphere above Utah, captured in the air like some of the other missions, like Stardust was attempted to capture through the air, and a number of spy satellites have done that. And then they're going to take it to a sample lab, the same type of lab where they studied the moon landing samples. And from there, we'll be able to learn much more about this asteroid. Hopefully that will all work out well. But it's been a really exciting week here. Asteroids are hard to determine their path, and we have to constantly study their path. If we have years of data on them, then we can start to predict their path. But even Mars, which is a lot bigger, a lot easier to study, 50 years from now, we have an uncertainty of, I think, 100 meters on where its exact center is, which isn't much, but with an object as big as Mars, you'd think we could do a little bit better than that. Thank you guys so much for joining me. Let me know whatever questions or comments you guys have. Until next time, keep on tracking and take care.